Good morning, everyone. Today we're going to talk about CVD, that is chemical vapor deposition. And we have two sessions. The first session we talk about the chemistry and fluid dynamics. Deposition includes mainly two types: physical vapor deposition and chemical vapor deposition. Physical vapor deposition, PVD, has evaporation, thermal evaporation, beam evaporation, and also sputtering deposition. We discussed in last two sessions. And chemical vapor deposition includes APCVD, RPCVD, PCVD, HDPCVD. See, I guess you can guess what their name means. Like APCVD, atmospheric pressure, CVD, LP, that is low pressure, and PE, this plasma enhanced, and HTP, this high density plasma, CVD. So the chemical vapor deposition is the process that the thin films are deposited onto the surface by thermal decomposition or reaction of gaseous compounds. Typically, chemical vapor deposition is performed in furnace. It's very like oxidation and diffusion we have discussed before. In some newer reactors with single wafer process, and we can use chemical vapor deposition to deposit a lot of materials like polysilicon, dielectrics, and some metals. Dielectrics include typically like silicon dioxide and silicon nitride. And the metals, typically refractory metals like tungsten. So chemical vapor deposition process is much more complicated, much more complex than physical vapor deposition. And we are going to begin with our simple or simplified thermal CVD system for polysilicon deposition. So in this simple CVD system, like here, so we have gas inlet and we have a gas exhaust. And this is a chamber, this is a reaction chamber. And in this reaction chamber, we have a susceptor. On top of it is a wafer. You can see this is schematic is very similar to diffusion or oxidation process or chamber. And for the gas, we have an example of silane. The silane, Si-H4, in gas format or gas phase can decompose to silicon in solid phase and hydrogen molecule in gas phase. So this is a simple equation, chemical equation, but actually there are many reactions happening. And this is only their final, this is their overall reaction or equation. So with this silane moves along the wafer, because the consumption to the wafer, so their density, their speed, the density can be changed. So in order to improve this the rate uniformity, usually we dilute the silicon, this silane, in hydrogen gas. For example, we can have 1% silane in 99% hydrogen gas. And this hydrogen gas we call it diluent, or it is inert carrier gas. Once the flow goes into the chamber, there will be a list of processes. And this is the whole CVD processes. So it can be divided into 7 steps. So firstly, we have the precursors, like silane, from the inlet, move to or transport to the proximity of the wafer, the first step. And then there might be some reactions happening to change this gas to further doctor molecules. So we are going to discuss later. For example, silane, so SiH2 from SiH4. And then, so we're going to transport these reactants or doctor molecules to the surface of the wafer. This is step 3. So at this surface, wafer surface, some chemical reaction will happen to release, and for this example, silicon. So we have some hydrogen molecules or atoms. These hydrogen molecules, atoms can absorb at the surface of silicon wafer. So we want to remove this hydrogen, and this is a desorption process of the gaseous byproduct. This is step 5. So next, step 6. So we transport the byproduct, like hydrogen, away from the surface of the wafer. Finally, we transport byproduct from the reactor to outside. So this is the whole process for CVD. And of course, these mainly are, so this can be thermal, can be plasma enhanced. This is basic 7 steps for CVD process. So during this process, there are 2 types reactions. So we have, for example, the gas may move over the wafer. Like here, we have the gas stream. Typically, the wafer or the receptor is at a high temperature, and the wall is cold wall process. And later we'll talk about high temperature process, high wall process. So high temperature wall process. Here, this is a hot wall temperature. Here we assume the cold temperature, cold wall process. So the wafer is very hot, and the reaction will occur at the wafer surface. But when the gas approaches to the wafer, actually the temperature there is high. There can be some reactions happening. So this reaction, chemical reaction, can generate solid, and this solid will land on the wafer. So such kind of process generated silicon is pretty poor. The uniformity is poor, and a lot of particles. And this typically is an undesirable process. But of course, so there are some situations it is good, but generally speaking, this is undesirable. A second type of reaction is solid surface reaction. So this is a desirable, favorable reaction happening at the surface of the wafer. So solid will form on the wafer surface. And this is actually the desirable deposition process. And we call it a heterogeneous process. And for gas phase reaction above the wafer, it's called a homogeneous process. For the reaction above the surface of the wafer, we suppose here we have a volume element here, dV. And here this dV is in the gas flow, and at some point above the wafer, and here we have the chamber wall. And one of the reactions, there are many reactions. So one of the reactions is for silane to decompose to silane, so SiH2 in gas form, and also hydrogen atoms. So based on law of mass action, so we have this Kp equal to P, this is pressure, so silicon silane, so SiH2, and the pressure, SiH2 pressure, and then we have H, is a hydrogen pressure squared. So here, because here we have a two-part hydrogen atom over the pressure of SiH4 silane, and this should be a constant at a certain temperature. It is a function of temperature. If temperature is set, then it's a constant. And this is law of mass action for this reaction. And we assume there's only one reaction here. We haven't considered the other reaction yet. And the Kp, so this is a kind of a parameter associated with the temperature. Is equal to K0, this is a constant, e to the power, this especially as Arrhenius function, as we say a lot. E to the power minus delta G over Kt. So delta G, this gives free energy, meaning the transfer from one body to another body, so that there is a maximum energy that can transfer. So this is free energy that can be transferred to delta G. So over Kt, and then Kt, this is a Boltzmann constant and the temperature. So for this one reaction, the total pressure will be, we have, let's say what component, what gas we have. So we have for silane, so we have silane, so SiH2, and then we have for hydrogen atom and hydrogen molecules. So we add them all together, it will be equal to P, the total pressure. The total pressure, so if we assume there's only one reaction inside the chamber, and then this pressure should be the inlet pressure, and this is constant. And we can control it, we can measure it. Third thing left is the silicon over silicon to hydrogen ratio. So this ratio actually decides, this is actually decided by the gas flow. So we can measure the gas flow. So the gas flow, so we have silane gas flow, and then we have for, silicon, so this is, we only have, silicon in, here the inlet, we have SiH4, the silane, so flow of silane, so one part. And then we have for H, this is hydrogen. It exists, it's in this like SiH4. This is the silane flow, and we have hydrogen flow. In hydrogen flow, there are two atoms, so multiplied by 2. And this is the ratio from the inlet. And then in equilibrium, so we have for the pressure, the partial pressure of silane. We also have like so partial pressure of silane of hydrogen. Okay. And so we can have 4 times the partial pressure of silane, because there are 4 parts of 4 atoms in this molecule, 4 atoms of hydrogen in this silane molecule. And then for hydrogen atom, one part, and for atom, for the molecule, there are two parts. So this one can be calculated based on their flow. The flow we can control, silane and hydrogen we can control. So basically, we have three parameters, three anodes. So the pressure of so 1, 2, 3. So partial pressure of acetylene, partial pressure of silane, and then we have partial pressure of hydrogen, and then we can solve for it. And then next important thing is the surface reaction. So the surface reaction. So this one, so basically we have one reaction. This reaction mainly happen somewhere above the wafer. And then at the surface, when this acetylene and silane approaches to the wafer surface, so the molecule, like acetylene, will be absorbed. And we have for gaseous phase acetylene here. Here A means absorbent. Yeah. So this absorbent, so is so meaning this the acetylene attached to absorbed to the surface of silicon wafer. And then this absorbent form of acetylene will decompose to silicon in solid form and hydrogen in gas form. And actually you can see we have the silicon deposit onto the silicon wafer. And this is polysilicon deposition. So normally the surface of silicon wafer is covered with hydrogen, and this hydrogen can be physically absorbed hydrogen molecule at low temperature. It can also be chemically absorbed hydrogen atom at a higher temperature. And then these hydrogen atoms or molecules need to dissolve, need to be removed and introduced out of exhausted, introduced out of their chamber to be exhausted. And this is the surface reaction process. There are many more surface reactions and reactions above surface. And basically we are just focused on their overall reaction. So these are other surface reaction not. So in order to get a full, better picture of the process, we need to discuss those more surface reactions. But here we just simplified to this overall surface reaction and the reaction about their surface. So here we have example, maybe we'll talk about later. So at the end of the class, we may have extra time. So we discussed the reaction, chemical reaction about the surface and on the surface. So next, we want to talk about the gas flow. So for gas flow, we have our simplified parabolic gas flow model. So the gas flow is important because it determines the transport of the chemical species. And it also plays an important role in the temperature distribution in the gas. On the other hand, the temperature distribution of the gas can affect the gas flow. So for high temperature, we need we need to control. We can control the gas flow, and we need to control the temperature. So if the gas flow satisfy some certain conditions, and it can form laminar flow. So firstly, suppose there, and generally it is the condition is that lambda, this is their free path. So mean free path, free mean path anyway. So lambda must much smaller than chamber dimension. So for example, the length of the chamber, the mean free path lambda must much smaller than chamber length. And this is normally true for CVD, chemical vapor deposition condition, pressure, temperature conditions. Also, the flow velocity U must be smaller, much smaller than the speed of sound, CS. And then in this condition, so we have laminar flow. Laminar flow, you can see, so here, at the beginning of at the inlet, it is uniform. And then when it flows into the chamber, and we suppose this this chamber, this tube, this maybe a rounded tube, circular tube, so it is very uniform. And then at the surface, on the surface of the chamber, the speed is 0. And then it will increase to the center of the chamber. And at the right at the center, the velocity, the speed of the gas flow is maximum. And then it will increase slowly, and actually it follows the parabolic law. So it's shown here. So this is the velocity of gas flow as function of R. This is the radius, and along the radius. Yeah. So this is equal to 1/4 eta dp/dz. So eta here, this is kinematic viscosity, and dp/dz is a gradient of pressure. And then A, this is the radius of the chamber and tube, and then R, this is the distance from the center. So and then when R equal to A, that means 0, right? So 0. So there is no the speed is 0, and then at the center, it's a maximum. Is maximum. Okay. So for the uniform flow to change to this laminar flow and to be stabilized, it takes some time, and this distance is approximately equal to A/25 N RE. So we have A. This is our tube radius, or chamber radius, and then we have the N RE. This is Reynolds number. So Reynolds number decided by U. This is maximum speed. Maximum speed. The speed. Okay. The speed of the flow velocity. And L, this is characteristic length of the chamber, typically divided by A. So A, this is approximately equal to A. A, this is the radius of the tube. And then mu, this is kinematic velocity viscosity. And eta here, real mass density of mass and mass density of gas, and dynamic viscosity of gas. Okay. Yeah. And this is the parabolic gas flow model, simplified parabolic gas flow model. And so Reynolds number should be small. If it is too large, actually there will be turbulent, and typically there's undesirable. So we just ideally we think it's uniform. So laminar flow. So look at this one first. So this is this line is the actual flow. This is the gas flow velocity, and this is the distance above susceptor over the wafer. the distance. So if it is far away from the wafer, and then we have maximum speed. This is the inlet flow speed. So just like look at here. So it's far away from the wafer, and we'll discuss why this is tilted. So the flow is uniform, far away from uniform. We suppose, for example, this is U infinity. And so because it's very far away from the wafer. Okay. And then close to the wafer, it will decrease. And then at the surface of the wafer, on the surface of the wafer, this gas flow will be zero. This is based on this model. We have discussed parabolic gas flow model. Okay. This is the real actual, this is the actual flow rate, gas flow rate. To further simplify the model, so we can suppose there is a point, there is a thickness, there is a distance from the silicon wafer, the surface silicon wafer. So at that point, for this point, below this point or the thickness, we suppose the gas flow velocity is zero. And above this thickness, the flow rate is U infinity. So we just so further simplify. And this basically this is the stagnant region or thickness. So because in this region and this thickness, there's no flow. And then there's some diffusion process. And actually, we may discuss this. You can see actually it's very similar to oxidation. We discussed before. Oxidation is kind of a thermal growth process, right? So a little bit different. So here we have actual flow. We simplified to this stagnant layer approximation. So in this part is the gas is stagnant, and then above that it's just basically equal to maximum the flow rate. Okay. So you can say in this second figure, here this is distance along the susceptor. This actually is supposed for the first figure, this is in Z direction or in Y direction. The second figure is in X direction. It is along the silicon wafer. And then we calculate this boundary layer thickness. So using this equation, it is actually increase along Z. Basically, this is 5 times square root mu Z over U infinity. So it is a function of square root Z. It's proportional to square root Z. So Z, this is here along this direction, along the wafer. Along the wafer, so we have Z, and then it will increase. So you can say when we increase Z, and we are going to have boundary thickness taller. Actually, boundary thickness taller. So in order to get uniform diffusion, uniform deposition rate, we will tilt this susceptor. And in this way, we get uniform boundary layer thickness along for everywhere for silicon wafer. Everywhere we have a same thickness of stagnant layer, and that's why we use tilted susceptor. So nothing to point out is gas phase diffusivity. So gas phase diffusivity, dE, is proportional to T to the power 3/2 time Pg, this is partial pressure of gas, and then P, the total pressure. So you can see it is proportional to T to the power 3 over 2. So this is for gas phase diffusivity. And you remember for bulk diffusivity, it's actually increased exponentially. So this is much faster. So in comparison to bulk diffusivity, the gas phase diffusivity is much less. The sensitivity is much less. The diffusivity is much less than bulk diffusivity in a function of temperature. Okay, so we talk about the chemical reaction, and we talk about the gas flow. These two very important process for deciding the the deposition rate. So for deposition rate is quite complicated to calculate. You need fluid dynamics. I need a chemical process. So we have our groups simplified model. So group actually we talk about oxidation. So we use a Deal group model, if you remember. So this CVD group model is very similar to Deal group model for oxidation. The derivation is kind of beyond our course. So actually in the textbook did not discuss. So I just write the final result here. So if you look at it here, so you have a silicon wafer, and we have this is the boundary layer or the stagnant layer, and on top of it, that's a uniform flow, gas flow. And here, this is stagnant layer, boundary layer. There's no flow. There's only diffusion. And Cg, this is their concentration, gas concentration. Above this is stagnant layer, and Cs, this is the surface. At the surface, and of course there is gradient, and that's why we have a diffusion. So and then we have flow. So the flux, diffusion flux, F1. So from in this boundary layer, and F2 is from the boundary layer into the silicon. And these situations are very similar to oxidation process. And we can finally get this deposition rate, flux, diffusion flux over the number of atoms per unit volume in the film. And this is equal to Ks Hg over Ks plus Hg, Ct over N times Y. And here we have a list of parameters explained. So Ks, the surface reaction rate, Hg, mass transfer coefficient. And Ks, need to point out, Ks equal to K0. This is Ks equal to K0 times exponential E minus EA over KT. This is our Arrhenius function. Yeah. So actually, anyway, so Ks is actually our exponential function of T. And then consider this simplified growth model, and consider this HS and HG, KS and HG. HG, this mass transfer coefficient. So we can say if KS surface reaction rate is much less than mass transfer coefficient, and then we simplify to Ct over N Ks Y, and it's proportional to Ks. So Ks, this is surface reaction rate, increased exponentially with temperature. Then we can expect in this figure, this is 1 over T. So, and then here temperature is low, and then here temperature large. So this growth rate will increase exponentially. Here this is log scale. Okay. So here, so that's why it's linear function. it will increase exponentially. And this region we call it reaction control, surface reaction control region, or reaction rate controlled region or region. And on the other hand, if we have Ks much greater, much larger than Hg, so the surface reaction rate is Ks much greater than Hg, Ks. And then we are going to have for this expression, this Ct over N Hg Y. So you can say here in this expression, there's no Ks, meaning it is not a function of temperature anymore. It is constant. The growth rate, growth velocity is our constant, no longer a function of temperature. And this region we call it mass transfer control. Mass transfer control meant by the mass transfer of the gas molecules. So here we say this will be the straightforward deposition rate as function of 1 over T. So we have reaction rate limited region or our region, and then we have mass transport limited region. And in this figure, it shows the rate, the deposition rate is also increases. It's also increased with the flow rate. So if the flow increase in this transport mass transport domain or region, so if we increase the flow, of course, the rate will be increased. Deposition rate will be increased. So for this two regime, at low vapor temperature, so the deposition rate increased exponentially. And the limiting step of the process is the reaction rate. So we need to have excellent temperature control and temperature uniformity to control the rate. So for this regime, it's primarily used in large batch system, where many wafers are processed at relatively low rates. So in this region, the flow dynamics are less concerned. So long as the temperature so long as the temperature, so this flow dynamic will not affect the temperature. Okay, and then flow dynamic is not a concern. So on the other hand, if the flow dynamic is too serious problem, and then it will contribute to the temperature uniformity, the non-uniformity across the wafer. Okay. And in this situation, we can use hot wall CVD reactor. And this region for at high temperature, so we have for the mass transport limited region. And deposition rate is proportional to 1 over the stagnant region length width. Okay. So, and in this regime, the limitation is the diffusion across the boundary layer. Also, the temperature dependence of the gas phase is much lower than the activation energy of the chemical reaction. The concentration of the gas controls the deposition rate. And we need to have excellent control of gas flows. So we also need to carefully design the chamber geometry to make sure we have a uniform transport to all parts of the wafers. And often this is used for single wafer or single small batch system. Okay, so this is a reaction limited region and a mass transporter limited region. So I only have 5 minutes left. I guess I don't have enough time to talk about this example. Maybe we can discuss the example in next lecture. Okay. I'll see you Monday.